How are you?
I'm tired.
Ah,
How are you?
I'm doing well, thanks.
Are you going to do MANOVA today?
You bet.
Cool.
So it looks like Leah is putting together a event for Saturday, right? She's putting together a, I think it's a Saturday,
Oh, yeah,
the Porsche Cafe.
Yeah, I've never been there.
I've not been there either. It sounds great.
Yeah, I need to try it. Are you not doing more today?
We have no more TED-Eds in S&P, and we have a small number of TED-Eds left for this course, but not this week.
Okay.
So today is just hands-on to set you up for tomorrow. You already have Friday's assignment. We'll have a TED-Ed for our final journal club, which will be on one of Dr. Weiss's articles with one of his students. And then I think we'll have TED-Eds maybe for the last couple of days. We'll have 3 days after that. I'm not sure how many of those we'll have TED-Eds. Probably at least 2 of them, I would guess.
Okay.
One is going to be on logistic regression, and one is going to be on different kinds of non-parametric tests. And so I think the TED-Ed will help our conversation. Good morning, everybody.
Yeah, so I was just wondering. Oh, really? You go home after that?
Yeah, if I want to.
Yeah. Still baby? It's nice to see everything here. Oh, I have another one. When is that? Oh, Thursday. Okay. One other. One other. What? People put like camel papers.
Wow.
Like and Tom. He's into it, that idea. Okay. Or like, Johnny is just like. We have common in color papers. Yeah. I sat for mine, but that was a special case. Yeah. Yeah, I remember it was just very nice. I got some and got them out. And then we started sharing and my mom had some kids. So you can go through copies that I brought. And just take out on my day.
Hi, Shelby.
Still on one side.
Yeah.
Oh.
But then, that muscle comes into like training. I usually not keeping it.
Ooh, fun.
Is it like a
Good morning, Jake. We'll get started in a couple of minutes. We will need SPSS today, and we'll also need Excel. So if you want to pop open just a blank copy of SPSS, that might save us a moment or two.
Yeah. I want to also, you want to study after that? Yeah.
Hi, Karen. How you doing? Good. Please, yes. Okay, well, we do have 8:30, so why don't we get started? Good morning, Psych Stats.
Good morning.
Welcome to the penultimate Wednesday of the semester. So we've really made a lot of progress, and we're almost all the way there. In just a couple of minutes, it might be the case that Dr. Dow joins us. So if you see Dr. Dow walking in, don't be surprised by that. She was planning on joining us. Maybe she's just a moment or two late, but we hope to have her joining us today. Okay, lots of great news. So the best news is that tomorrow we have a quiz, and that will take the entire period. So let's give it up for the quiz. Yay, right? Okay. And then the even better news is that the day after that, we have an exam that's due, and that's our take-home exam. So it goes quiz and exam. All right, so that's our typical Thursday, Friday sequence at the end of a section for us. So just to remind you, you were given the handout for the exam, and here it is. This is going to be, again, one of the uploadable files onto Blackboard. And you're going to be integrating ideas. We'll talk about integrative complexity, how you're going to be able to pull some of these ideas together that speak to the issue of replication. That's come up a few times. We have this very recent paper that came out in Psychological Science just before we went off to Thanksgiving break. And so we've incorporated that here. We also have signal detection theory and also a little bit about Bayesian statistics and introduction to that, which is in a way related to some of the main ideas in signal detection theory. So we hope that you enjoy putting all those together, and we'll have our writing workshop also on Friday as we typically do. So please bring a printed paper on Friday in addition to uploading that. Okay, we've done that many times before. Okay, I'd also like to just set the stage a little bit for tomorrow's quiz. You are now pros at these quizzes, same kind of format as always. Low stakes test, just 5% of the grade. That is 1/32 of your overall GPA. That won't matter 3 years from now. Okay, so low stakes, very definitely, but the same format as always. The content will be computational, and we're going to be focusing on Excel and SPSS computations. This is the stuff that's going to be new since the last one. Just to remind you, we'll do some signal detection theory exercises today so that you're very comfortable with those. And some of these Excel commands you've already used, the norm in function, norm dist function, and some of their near cousins called the norm sin and the norm sdist. We've used those, but not too recently. So we'll go back and we'll review those, and we'll see how they link up to signal detection theory today. And then I'm really excited that I think TED Ed has kept us right on track. We've done ANCOVAs already. We've done factor analysis. I'd like to reserve about the second half of today to do relatively simplistic MANOVAs. Excuse me. So when I say a simplistic MANOVA, we'll take a simple case where we'll compare two groups of people. But instead of comparing them on one dependent variable, we'll compare them on many, many dependent variables. So that will be our introduction to MANOVA, and we'll do a couple of examples so that you're very comfortable with that. And then that will take us through the rest of today, and then we've got the quiz tomorrow and also the exam on Friday. Welcome, Dr. Dow. Thanks for joining us. You're welcome to log in if you want. I sent you a couple of files, and you can play along, too, if you want to play along with us. Okay? All right. So any questions on where we're going for the next couple of days? So a little review. Dr. Dow was setting them up for us. Tomorrow is a quiz in here, and Friday is an exam that takes the form of a writing workshop. They've been given a prompt, and they go on the back table, and we pass around each other's papers, and we do some workshopping on the papers. That's what's going on for this week. Okay, so what we wanted to do is get back into the concept of signal detection theory, and I realized that we hadn't talked about signal detection theory since just before the break, but we spent the Friday before break talking about signal detection theory, and we went through this entire PowerPoint. Now, that gave us a lot of conceptual background for signal detection theory, And some people in this room have also done signal detection theory in S&P. What's unique about it in this class is we do the computations. This is a stats class, so now we actually run the computations rather than just the ideas. So let's just remind ourselves about some of the main ideas. Can somebody tell us what are the two primary statistics that come out of signal detection theory? We compute two things. What are those things? Yell them out if you remember. ROC curves is one of the things that we're going to pull out. In an ROC curve, we have actually two things going on. Right? The two main ideas from signal detection theory. Maybe this helps. What is this? D prime. Okay, right. D prime. And can somebody remind us what D prime tells us? At least approximately. It measures what? Yeah, thanks. Okay, an individual sensitivity to stimuli is how we would think about it in sensation and perception. And we all had a sensation and perception component in Psych 100. But you can also think about it as a sensitivity of any system. It can be a sensory system, but it can be the sensitivity of a judicial system. It can be the sensitivity of a system for bringing students into the college, an admissions system. It can be any kind of classification, really. We can talk about the sensitivity of an instrument in figuring out who has depression and who doesn't have depression, who really is experiencing schizophrenia and who isn't, who should be receiving a diagnosis of ADHD or any other kind of clinical condition, and who should not be receiving that diagnosis. So we can think about the sensitivity of an instrument, the sensitivity of a particular counselor in making those decisions, and we can also pull out the other component, not just D prime, but our other idea from signal detection theory was, let's yell it out, beta, okay, right? So beta, and that tells us about the bias that we might have in somebody's responses. If we're talking about an individual responder, it could be the bias that a particular instrument has. An instrument might be relatively liberally biased or conservatively biased, okay? So those were some of the main ideas, and then we got to some of these distributions that bring us into the stats world. And just to remind you that some of the inputs are going to be coming from here. I'll make this really big. In the simple case of, we'll take an S&P experiment, we have a stimulus that's either present or absent, and your job is to report that yes, it's there, or no, it isn't there. And we have this little 2x2 matrix that gives us something very familiar to us in this class because we know about type 1 errors and type 2 errors, different kinds of correct responses, different kinds of incorrect responses. Okay? And we can convert that into something that looks more like this. I'll fast forward a bit. Okay, so this is something that we walked through the other day. Can somebody remind us what the 0.5 and the 0.5 are doing over on that right-hand side? What are those telling us? Where do those numbers come from? This might prompt your memory a little bit. If we now move the criterion leftward, those numbers change. So now we've moved this criterion to the left. We've got a 0.2 over 0.6. We can move the criterion to the right, and those numbers now flip. We've got a 0.6 over 0.2. Where are those numbers coming from? The 0.6s and the 0.2s, 0.5s? Can't tell if we're on the floor or the ceiling. Sometimes we get it. How many people are not remembering where those numbers came from? If we're not remembering, okay, so we're on the floor, we're not on the ceiling. Okay, so what we're doing here is we're saying that this is going to be some kind of likelihood ratio. Okay, this is going to be the way that we quantify the criterion, the second of two statistics that we pull out for signal detection theory. And the idea is that at this criterion, this is the level of neural activity that we would need in this case to distinguish between a yes response and a no response. Some responders are relatively liberal. They require low levels of evidence, low levels of neural activity for them to say yes. Others are going to require a higher criterion and a higher level of evidence, and so we're going to have something like this slide back over to the right, and they will say yes or no, but they now have a higher standard, a higher criterion for saying yes or no. Okay? Now where these numbers come from is all dependent on where this criterion is intersecting these two different distributions. You might remember that we have the noise-only distribution, the signal plus noise distribution, and by convention, we take the probability associated with the right-hand distribution, that's the signal plus noise distribution, and we have that at criterion. And what we're estimating here is that where this line is intersecting that distribution, I'm going to go over to the y-axis, I'm going to call that a 0.6. Okay? And you might notice that for the left-hand distribution, the same vertical line, the same criterion, is intersecting the left-hand distribution, which is the noise-only distribution, at a much lower level. And I'm going to call that 0.2. Okay? Some people are following that. Is that working? Does that all sound familiar to us from the other? So what basically happens is, as we move from somebody who's relatively conservative to somebody who's relatively liberal, I'll go back one to show you the more liberal response, we just get a reversal of those numbers. It's still 0.6 and 0.2, but now, in this particular case, at criterion, this level of neural activity is more likely associated with the left-hand distribution than with the right-hand distribution. The right-hand distribution is over here. Its intercept at criterion is going to be about 0.2 versus 0.6. And by convention, we put the signal plus noise distribution's likelihood in the numerator, and the noise-only distribution, that likelihood goes into the denominator. Okay? So then, as Hannah correctly noted, we did come to receiver operating characteristics. Okay? And we said that all points along this line correspond to d prime equals 0. I'll keep my hands behind my back. Can you show me d prime equals 0 by gesticulation? What is d? Okay, there they go. Right? I think most of us are doing that. Yep, okay. Can you show me d prime equals 1? Just as an approximation. D prime equals 1. Okay, there they go. And let's go to d prime equals 3 and 2. Okay, so we're going further and further apart. These distributions are becoming more distinct from each other. Okay? So in our receiver operating space, here's now a curve, a receiver operating curve, that corresponds to d prime equals 1. And then all of a sudden, in the next slide, we had these tennis balls land on our operating curve. Can somebody remind us what those tennis balls are doing? Got 3 of them there. What are the 3 tennis balls doing? And maybe you can tell us how they're similar to each other, how they're different from each other. Let's break that down. How are they similar to each other? I'll yell it out. Mum, 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 mum. Mum, 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 mum. They're all similar to each other because they're all tennis balls? They all have a tangent point, okay. Thanks, Jake. Yeah. They're all on the d prime equals 1 curve. They all have underlying distributions that would look something like this, okay? So no one of them is more sensitive than another. These might be 3 different people, right? Okay. Will somebody remind us what we would say about this particular one? It's on d prime equals 1, okay? So that's true for all 3 of those, okay? Its tangent curve is, tangent line, is relatively steep, okay? So it's going to have a steep slope, okay, and that's going to correspond to a relatively conservative or high level of criterion. Okay, so this is going to be, the steepness of that tangent line is going to be proportional to the criterion. If we go to the other extreme, there's that upper tennis ball, and now we have a tangent line that is going to be quite a bit shallower. Okay, so it's going to be some slope less than 1, and we remember from our earlier conversations that liberals have response biases or criterion that are going to be less than 1 when we think about the numeric values associated with beta. Right? Beta, for a neutral beta, we would be at 1, and if we're liberal on the left with low criteria, we're going to be less than 1. If we're conservative, we're going to be more than 1. Okay? So it comes back to these ideas over here. Right? Here's our relatively liberal diagram. This person has a liberal response bias. They're going to have a criterion value that is going to numerically be less than 1. Here was our neutral person, okay, 0.5 over 0.5. Here's our conservative person. We have 0.6 over 0.2. So we're going to have different kinds of slopes associated with these tennis balls here on our receiver operating curve. Show of hands, who's okay with that? Remember, yeah, is that all looking familiar? Okay, so what we wanted to do today was spend most of our time just reminding ourselves what was going on here conceptually, and then we're going to try to now pull off the computation, setting us up for tomorrow's computer quiz. Okay? Just as one more reminder, before we go off to Excel and do these computations, we're going to take advantage of some Excel commands computationally that we've seen before but we haven't seen in a while. So we're going to remind ourselves of what these are. First, we're going to try to come back to these 2 primary indicators inside of signal detection theory. And one is D prime. And this is where we speak French, as we always do. Z hits minus Z false alarms. Everybody say it with me. Z hits minus Z false alarms. Now what we have readily available to us as psychologists, we will always know proportions, the proportions of hits that the person had, the proportions of false alarms that they have. So we're going to take advantage of an Excel function, we're going to stick in some proportions, and we're going to get out z-scores. We actually did this even as early as September, but we haven't done it maybe since September, so we'll return to that. And we're going to stick in a proportion associated with our hits, we'll get out a z hits. We'll stick in a proportion for false alarms, and we'll get out z false alarms, and we'll difference those two, z hits minus z false alarms, and that will be a quantitative estimate of d prime. Who's okay with that? Yeah? Okay. Something almost as simple for the other major idea, this beta indicator of the criterion. We're going to, again, take two numbers, one associated with false alarms, one associated with hits, but now we're going to do something just a little bit different. We'll call this a probability density. And a probability density is the instantaneous probability that you might remember from back over here. So at this particular instant, that particular point, what is the probability associated with the left-hand distribution? What is the probability associated with the right-hand distribution? We might even call those likelihoods. This can be thought of as a likelihood ratio, and we're going to use the cousin command here for determining beta. We're going to use the norm dist function as opposed to the norm in function. We've done that many times before. We've done not only norm dist, norm in, but we've done t-scores, t-dist, t-ind, chi-square scores, chi-ind, chi-dist, f-scores, f-ind, s-dist. Who remembers doing all of that? Okay, so we're going to now use the normal curve, dist functions and in functions. We're going to stick in, at this time, a z-score associated with hits. We'll get out its density. We'll stick in the z-score for false alarm. We'll get its density. We'll take the ratio of those two densities, and that will be our estimate of beta. Okay? So that's something that we've seen before, okay? But I realize it's been since Thanksgiving break since we looked at that. Okay, so let's put that down just for a moment. And if you'll join me out on the S drive, we'll go to the signal detection theory practice set. And if Dr. Dow would like to play along, she doesn't have to, but I emailed that to you so you can open up that as well. And we have different tabs. While people are calling that up, and our students know where those things are, if you go out to our S drive, we have a whole bunch of practice sets, and one of the practice sets is labeled signal detection theory exercises. So we'll go through a few of those, and then in a few minutes, we'll make our way over to MANOVA. We want to reserve some time for that too. Okay, so we're in signal detection theory, and just for Dr. Dow's information, the way we typically run through these Excel sheets, Dr. Dow, is we might have 10 of them, 10 different tabs. Tabs 1 and 2 are basically the same. Here's the problem. Here's the answer key right next to it. So if you ever get stuck, you're always allowed to cheat and click over here, and not only is there a full answer, but you can also click in. You can see where the genotype is for that, what actually is driving that computation. So we're going to pretend just for a moment that we're not looking at the answer key, and we're going to pretend that it's tomorrow, and Dumbledore is our participant, and we're going to try to do a D prime on Dumbledore. Given that, and I'll turn this down just a little bit. Okay. Given that Dumbledore was taking some data for us, and Dumbledore had a hit rate of 0.8 and a false alarm rate of 0.01. How many people are there on that sheet? Okay. So what was our little saying for how we compute D prime and speak French? So yell it out again. What was our saying? Z hits minus Z false alarms. So what we need to do somehow is to develop a Z score for hits, Z score for false alarms. Let's join me, if you will, in cell I, and that's I7. Okay? And I'm just going to begin to label that Z hits, and then right next to it I'm going to put in Z false alarms, or ZFA. So I need to get a Z score associated with those two quantities. If I difference those, I've got D prime. Okay? How do we get computations going in Excel? Equals sign, okay? Equals. All right, and now we're going to put in the norm in function. Again, we've used the T inverse, the T dist, chi-in. So here's norm. And the reason we're using norm is because these are all Gaussian distributions that we're presupposing in signal detection theory. That's often a presupposition for t-tests and ANOVAs and so forth, that you've got some kind of Gaussian distribution. Okay? The probability that Excel is prompting us for, that's equals norm in. And let me just zoom in a little bit so Dr. Down might be able to see us a little bit more effectively. Excuse me. Okay. I'm over here for Z hits equals norm in. Okay? And we get prompted for a probability, and the probability is really the proportion of hits. So I'm going to click right on the 0.8. Okay? And then I'll put in a comma, and I get prompted for a couple of other parameters. We will always use 0 as our mean for signal detection theory, yeah, we're going to assume that we have a zero mean in this hypothetical distribution. And then we also have to specify its standard deviation. Typically, and please don't put this in, we would use a 1 for reasons that might become clear in a moment. I'd like us to use as our standard for signal detection theory 0.5 as our standard deviation. So you can imagine having some axis that has a Gaussian distribution on it, centered at 0, and a standard deviation plus or minus 0.5. We're going to put in a 0.5 here. Just 0.5. Okay, and then we close that off. And I will leave that there so you can see what my genotype looks like. I'll let you hit enter, and you tell me what number you get. Can we all yell it out? 0.42? Let's see if I get that. All right, I got 0.42. So that's what we observe in our hypothetical experiment with Dumbledore. Dumbledore is hitting 80% of the time. When the stimulus is there, he'll say it's there 80% of the time. 20% of the time he's missing, but 80% of the time he's hitting. Who's okay with that? Yep, okay. Now, because we've developed this as a spatial relationship, we can do our little trick of grabbing the right-hand knob there. We can pull that over, and we can automatically get the same computation, but now it is referencing that particular cell, the P false alarms. So the z-score associated with 0.01 is minus 1.16. That's what we've got going on there, assuming that we have a standard deviation of 0.5. How many people get that number? Yeah, is that working for us? Okay. So one more time, really loud, if we go over to the d prime area, what was our formula for d prime in French? D prime equals? Okay, so it equals z hits minus z false alarms. Okay. And we come up with a Dumbledore d prime value of 1.58. So one way of thinking about this is that there is a 1.58 standard deviation separation between Dumbledore's left-hand distribution and the right-hand distribution. His distributions don't look like this, they don't look like that. They look like something like this that we might measure, and they would be 1.58 in terms of standard deviations apart from each other. Who's okay with that? Yeah? Okay. All right, let's do now the complementary computation that is going to be for beta. This is our indication of criterion, because if we wanted to plot Dumbledore on a receiver operating characteristics, we would know that he would land on the 1.58 d prime curve. We don't know just yet whether he's relatively conservative or relatively liberal. If he's perfectly neutral, he would have a criterion or beta value equal to 1. To the extent that he's liberal, he'll be less than 1. Liberals on the left with low criteria is our alliteration. And then to the extent that he's more conservative in his yes, I see it response on this test, he's going to have a d prime that's going to be greater than 1. Okay? So now we do need to get some densities. Sometimes these are called likelihoods, but we'll call them density for false alarm, and you can and for hits, and you can abbreviate that any way that you like. Somebody yell out, what was the name of the command that we used in this case? It's not going to be norm in, it's, which command? Norm dist, okay? So we're going to say equals, and this one's just a little bit different, okay? It actually takes one more parameter, so let's all do it together, norm dist, and I'm going to open a left paren. And mercifully, once we get the command name and we open a left paren, Excel prompts us for everything that we need, okay? So in this particular case, as you might remember from the PowerPoint just a moment ago, what we stick in is not a probability, but rather we stick in a z-score. So I usually like to compute z's first for d prime so that we have them handy for when we go to get data. So now we want the z-score associated with the hits, and that's going to be this one in I8. Who's okay with that? That works, okay. And what did we say our mean would always be for the signal detection computations? So we're going to put in a comma, 0. And what did we say our standard deviation would be? 0.5, okay, right. And I'll explain that in just a moment for why that's 0.5. Okay. And there's one more parameter, and this group I think would understand what this is. We had some TED-Ed questions a while back when we were talking about different kinds of distributions. Here's a Gaussian distribution. This is actually a non-cumulative Gaussian distribution, but you can take the Gaussian and start it up and bring it down again, or you can start it up and just have it accumulate. So there's the cumulative type, and there's the non-cumulative type. And this is asking us, which type do you want? Cumulative, yes or no? And we're going to say, no, we don't want it to accumulate. We want the non-cumulative, typical bell shape. That's what we had in our diagrams. So we're going to put in a 0 there. Okay? telling Excel that, no, we don't want that to accumulate. We want it to be bell-shaped, non-cumulative. So I'll leave that there. I'll let you hit go, and we'll let you yell out whatever number you get. What number do you get for density of hits? Okay, let's see if I get that, 0.56-ish. Okay, if we drag that one over one more time with the spatial relationship that we had just a moment ago, we now have a different number. This is corresponding to the Z false alarm rate. Okay, we stick in a Z-score, we get out a probability density, and then to compute beta, we simply take, again, two quantities, but this time it's the ratio of those two likelihoods, the ratio of those two probability densities, and that's going to be the density associated with hits divided by the density associated with false alarms. Okay? And we wind up with a beta value of 10.5 and some change. How many people can corroborate that number? Can I get an amen on 10.5? Yeah? All right. So is Dumbledore relatively conservative or liberal in his responding? Let's yell it out. Dumbledore is conservative because his beta is greater than 1. Okay, so he's going to be, way over. He's going to need a lot of evidence before he says, yes, I see it. Look how rarely he false alarms. He does false alarm occasionally, but only something like 1% of the time. Okay, is that working for us? Okay, we could compute also the percent correct. You probably know how to do that. Half of the time they have the opportunity to hit. When they do, they're doing it 80% of the opportunities to hit are actually successful there. Then what we could do is we could figure out how often they're correctly rejecting by taking the complement of the false alarm rate, but that's not directly related to single detection theory. So we could do percent correct, but I'd like to save our time and do some other things. Most notably, I'll ask you to join me by going over here to some intriguing examples. Is one of the titles over on the far right-hand side. I think you might get a kick out of this. I always find this to be intriguing. Okay. First, how many people are there? You got there? Okay. So this is now a set of data that is really just like the set that we did before. I have 4 different participants, A, B, C, and D. Again, I'm calling them participants, but these could have been instruments for classifying people for different kinds of psychological disorders. They could have been judicial systems. Okay. Here we're getting their hit and false alarm rates. I've computed their percent correct. Notably, participants A, B, C, and D all have exactly the same percent correct. They're all at exactly 75% correct. Who's with me so far? Yeah, okay. But they all have relatively distinct D prime values, or at least several of them are different from each other. Okay? So some of them have a D prime, that's a separation between these two of 0.67. One goes all the way up to 1.1, and yet they're both at exactly 75%. So what you can see through this example is that as beta is moving around, we've pulled out their bias and tried to report their genuine sensitivity. That's their D prime value. Okay. And that too is distinct from their percent correct. So from about 3rd or 4th grade, we've all gotten very used to percent correct. All of your tests are given back to you in percent correct. It's a very intuitive measure, percent correct. But it also is one that is somewhat vulnerable to fluctuations in beta. As beta is fluctuating, you can see in this particular case, percent correct is remaining the same, but we know that the genuine sensitivity is actually changing. In this particular case, participant C is quite a bit more sensitive than participant A, but because of the nature of their biases, we wind up with exactly the same percent correct. So the point that you'd like to take away from these 4 rows is that percent correct doesn't provide the same information as D prime. It's a separate kind of an indicator. D prime is a genuine indication of sensitivity. We have the complementary case all the way down here, and here we have 3 more participants, and they are called X, Y, and Z. And we have the same layout for these participants. Notably here, they have identical, or nearly so, D prime levels. They're all 0.674, or thereabouts, okay? But they actually differ from each other in percent correct. Here, participant X has 75% correct. Here is 70 or 71% correct. Okay? So there are some differences here in percent correct, even though they have exactly the same D prime level. So as scientists, we sometimes want to know what is the sensitivity of a system or of a classification instrument, and what is its bias, and we can put that instrument then on some kind of receiver operating curve, and we get quite a bit more information than we might have gotten through percent correct, which doesn't take into account these fluctuations that are attributable to biases and criterion shifts. And people are following all that? Yeah, is that working for us? Okay, one last bit, and we won't spend a lot of time on this. Now, those were some intriguing examples. The very last tab is called Some Random Examples. And one of our favorite keys on the keyboard here is F9. If you hold down the F9 key with me, we can make this thing spin. And now we start randomly generating all kinds of hit values using our rand command. Right? That gives us some number between 0 and 1. We're randomly generating false alarms. And then everything else here is set. Given those two pieces of information, we can derive %correct, d prime beta, and their helpers of false alarms in z-score space and also in density space. Okay. All right. So for tomorrow's quiz, we might ask you to compute some values that relate to d prime and beta based on a hit rate and a false alarm rate. Who's okay with that? Yeah? Okay. All right, so now that we've done some random number generation, I'd like to go now to something that I've not done with any of my classes before. This is the 6th or 7th time that I've taught stats. We've never really had the opportunity, typically, to get as far as MANOVA. But I would like to try a MANOVA with you. We'll keep it as a relatively simple MANOVA. We'll take a simple case where we'll compare two groups. And now because it's a MANOVA, it's going to be multivariate, which means we have more than one dependent variable. Okay? And specifically, we're going to be talking about latent variables. And first, who can remind us what a latent variable is? Okay, thanks, Gabe. Yeah, we have to have proxy measurements for it. Right? And so sometimes you can almost create a variable on the spot, something like good student. What makes for being a good student? Well, what we'll do now is go to an Excel spreadsheet that has lots of possible indicators of what makes for a good student, any one of which might be reasonable but maybe flawed in some ways. And we'll take now a whole bunch of measures, and we'll see if we can put them into a MANOVA and see what kinds of patterns we get. So we haven't used MANOVA before. So let's put this one away. We'll put the signal detection theory one away. And out on the same area of the S drive, you have one other practice set that's labeled MANOVA, and you have a handout on your desks. I don't know if Dr. Dow got one. One for Dr. Dow. Dr. Dow might already know the clicks for MANOVA, but they might not be handy. So if you wanted to play along, okay. We'll get to SPSS in just a moment. We'll give you a minute to pull out the file here in Excel that is called Multivariate Sampler. Okay? And we have 3 tabs here. We're going to start out with something that I call the purely random tab. And let me just give you the lay of the land here to help motivate this problem. So what I've done is I've created an A, just all these different participants. I'll let you tell me, how many participants do we have in our data set? Real loud? 300? Okay, so that's a pretty good sized data set, right? I've created 300 examples here, okay? And our between group variable is going to be gender, and I'm not going to say which one is male or female. We're just going to call the genders 1 or 2. I will ask you to join me by clicking into this particular cell, and this is going to be cell B2. And you can see that I'm taking a random number between 1 and 2. It gives us an integer of either a 1 or 2. If you'll join me by clicking on the F9, you'll see that we're just randomly assigning a gender to participant 1, participant 2, and so forth. Okay? Who's all right with that? We have a lot of random number generation here. In fact, after these two sort of marker variables, we have 10 measured variables. Gabby correctly pointed out that if we have this abstraction, this latent variable, that is sometimes called an uber variable that we think of as good student, you might say, well, one indicator perhaps is GPA. So I'll ask you to join me by clicking over here to GPA. And this is a fairly complicated formula that you see there, but again, we're taking advantage of the normal distribution, and we're randomly generating a score that has a mean of 500 and a standard deviation of 100. In the earlier versions of SAT, that's how that test had been normed. The mean had always been 500. The standard deviation had been 100. Typically, they would give you a verbal test. They would give you a math test, so I'm going to multiply those by 2 so that I have sort of the sum of those. And people would say that you could get a score that would be as high as 1,600 and as low as 400 for your combined SAT score. So every time you hit the F9 key, you get some randomly generated score. That is, again, independent of your gender, okay? But it's just randomly generated here. And then we can look at other kinds of indicators of good student, in quotes. And that might be a high school GPA. And we can take now a normal distribution of grades that are centered at 3 plus or minus 0.3 as a standard deviation. Okay. Some people are seeing that there's a 0.3 standard deviation there. Is that working for us? Okay. Here's our norm function. In goes some random variable. Our mean is 3.3. We're going to use the same kind of model for the college GPA. Let's pretend we have an attendance rating that goes between 1 and 10. Students who attend more get excuse me, values closer to 10. Students who attend less get values closer to 1. The same thing for teachers' conscientiousness ratings of students. We'll model it this particular way, 1 to 10. Then we have class participation grades that, again, are going to be normed to something like a mean of 70 or 80 or 85 as you move along here. So every time you hold down the F9 key, we generate tons and tons of new numbers for these 300 participants. Okay? And what we might ask is, on average, are there some differences between the two genders on the good student variables? And we have a whole bunch of them here. We have all these different variables. Okay, so what we need to do is somehow make our way over to SPSS in just a moment, and we need to first define the variables, and I've put them over here in column O. Can people just cursor over to O and make sure that you find the variables? Right? Those are all the different columns that we have. So we're going to define those in variable view, and then we're going to take this huge, huge rectangle that has 300 rows and something like 10 measured variables, and we'll paste all of that stuff in, and we'll see if we can run our MANOVA and how to interpret all of that. Okay? How many people have what they're looking for in column O? They have the different variable names. Okay? So why don't we go over to SPSS, and we'll start out that way. Well, let's put in all these variable names, and then we'll set the stage by doing that for plopping in this huge rectangle filled with somewhat random data, just to get a MANOVA going here. Okay? So I'm going to go over to SPSS. I'm going to go to variable view. And from Excel, I'm going to do my Control-C. I get the ring around the rosy going here. Okay, that indicates to me that it's in the memory buffer. And I'll go to variable view. I'll put on name, and I'll paste that in. And just like that, we get all of these different variables. We'll see by show of hands how many people have that. Okay. Now, one of the things we do like to do, because we do have an alphanumeric variable for participant, can somebody tell me how we change the type? Let's yell it out. We have to change the type designation. Okay, so we're going to go to, we can call this a string, okay, and that allows us to put in such things as P1s and P2s and so forth. Everything else can remain numeric, but this one goes to string. So I'll do that again. We haven't done that one in a while. We go to type, and we put in string, and now we can put in something like a participant 1 or something along those lines. Okay? And people have that. Yeah, we're good to go? Okay, let's now go over to data view. We'll put our cursor way up here, okay? And that's where we're going to paste this thing in just a moment. But now we have to go to Excel and grab this huge rectangle filled with information. And I'm going to go over here to P1. Okay, I'm going to drop all the way down. I'll hold the Shift key, and I'll go all the way over to L301. Okay? I've got that huge rectangle, and I'll do a Control-C to get the ring around the rosy going. Please make sure that you have all of that. Okay? Right. And when you're set, hopefully we won't break the bank. Sometimes this does take SPSS a little bit of time. Let's go back over here to participant, and we'll do Control-V as in victory. Interestingly, there's a huge pause, okay, because that data set is so big. I did it, okay, and then finally it catches up and it plops in all 300 rows of data, and I think we have about 12 variables here or so. Okay? Show of hands, how many people got that transfer? Yeah, did that all work for us? Okay, very good. So, just to set up the problem again, typically, much earlier in our semester, or even in Psych 200, you might compare men and women on any particular variable, any particular outcome variable or dependent variable. In the MANOVA, we now have the opportunity to do this on multiple variables simultaneously. So multiple analysis of variance as the MANOVA, multivariate analysis of variance. Okay? And you also have the cheat sheet in front of you that tell us how we get this analysis going. So like we have for most of our analyses, we begin by analyze. Then you tell me, what's the next click? General linear model and not generalized linear model, okay? So for the first time this semester, we're going to click on multivariate. When we did between subject cases, we went to univariate. When we did repeated measures cases, we went to repeated measures. Now we're going to click on multivariate. Okay? So I'll click there, and we come to this box, and by a show of hands, how many people are still there? They're on this box. Okay? So our grouping variable, this will be our fixed factor. We're going to go with gender, okay? And one of our genders is 1, the other one is 2. It doesn't really matter which is which, okay? So we're going to slide that one in. Right? And then participant is not a variable that carries relevant information about these good student indicators, but everything else here presumably does. So I'm going to click on SAT, and I'll hold down the Shift key. I'll click all the way down to writing assignment, and in one fell swoop, I'll slide these over to dependent variables. So now I have 10 dependent variables clicking on that one fixed factor, and we've got gender being 1s and 2s. Now remember, everything there was random. So your numbers are not going to be the same as my numbers. Your numbers will not be the same as your neighbors. Okay? Okay, just like we typically do, let's go to options. Okay? And we've done this many times before, we like to get means overall. So what's maybe the grand mean? And then we'll also get means specific to the two different gender groups. One group is a 1, one group is a 2. Excuse me. And then we have also these 4 items that we typically take. We take descriptive statistics, estimates of effect size, observed power, and we need to do our homogeneity test. See, what is the name of the homogeneity test? Levine, okay, right? So we're going to take a look at Levine's in just a moment and see how we do. How many people have that much? Yeah? Okay. So let's let it spin and run our first MANOVA by clicking on OK. We'll get some output. Okay. And now here, let's take it through box by box, because tomorrow I'll ask you to do these. The clicks are fairly easy, right? But interpreting all this is just a little bit more challenging. So in my particular between subjects factor, remember that people told us we had a total of 300 participants. In my particular case, gender 1 wound up with 154, and gender 2 wound up with 146. You probably have different numbers. Can you confirm, just by doing some mental math, that your two numbers do add to 300? Is that working for us? Right. So they're good. And they're probably pretty close to 150 each, plus or minus something. Did anybody hit 150 on the head? That could have happened, now that we have 10 people doing it, 11 people doing this independently, okay? But every so often that will happen, okay? And so just to begin to walk through the descriptives, we won't do all of it. Let's take one of the indicators of a good student. That's our latent variable, but one indicator is a measured variable of SAT, and we mentioned that those would have a mean typically of 500 for any one test. For the 2 tests, they would add up to a mean of about 1,000. You can see that our 2 genders are about 996, 985. They're probably quite similar, even in yours, to each other. Your numbers will not be, again, the same as mine exactly. Okay? And then we can do that for any one of the many, many indicators. Their homework grade, they were averaging 85% for one gender, 84% for another gender, and so on down the line. We will not need to look at the covariance matrix. Okay? In the interest of time, we'll skip over that. That will not be on the quiz, and that's not something that we need to concern ourselves for our interpretation. Okay, let's go to the multivariate test. And now it's been more than a week since we've talked about this, okay? But the one item that I really like you to look at is the Wilks lambda. Just by a show of hands, who even remembers that we talked about Wilks lambda? Okay, all right. So we talked about that a couple of times, including the chimpanzee music therapy paper, where we first saw the MANOVA. So you've seen MANOVAs before, but we actually hadn't gone through the clicks. Okay. So what we'd like you to do is, when you get to this multivariate box, and there will be on the test tomorrow, there will be a multivariate example, a MANOVA example. We can skip past the intercept. The intercept is simply telling us whether all the variables that we have are different from 0, and that's a relatively uninteresting outcome in this particular case. What we really want to know is Wilks lambda for our variable of interest gender group. And we'll go over to the Wilks lambda value, and we'll see that the Wilks lambda value is 0.976 for me. Let's yell, like, a few folks yell out your Wilks lambda values here for the gender group. Okay, right, so what we're seeing is probably these are relatively high numbers. You might remember that, well, maybe I'll let you tell me. What did Wilks lambda tell us? What kinds of information did Wilks lambda provide? We talked about it it was actually a TED Ed question for our chimpanzee journal club. But it's been a couple of weeks. I won't necessarily expect that you remember that one. This is the proportion of variance not explained. Okay, Wilks lambda, somewhat counterintuitively, is a proportion of variance not explained. So, if you'll join me by going over to the partial eta squared, you should find the complementary number. Right, the partial eta squared is the proportion of variance explained And if we're doing really well, we've got it all, that would give us a 1. If we're doing really badly, that would give us 0. So in my case, I'm explaining about 2.5% of the variance, 2.4% of the variance, and here's what's left over. Okay? And in my particular case, my sig value for this MANOVA is non-significant. How many people wound up with a non-significant sig value there? Is a sig value greater than 0.05? Yeah. Right? So measuring all these variables, we found these two genders did not differ from each other. Not too surprising. Why is that not surprising? Why would we expect to have a null finding here, given what we did in Excel? And people aren't sure. Everything in Excel is entirely random, so we randomly assign you a gender, and then we randomly assign you an SAT score, or a participation score, or a homework score, something like that. So given that there is just pure random numbers going in there, you wouldn't really expect to find a difference between the genders. Okay? Right? So, and when we add all these different variables together, we still wind up with a null effect. Okay, let's take a quick peek at Levine's test. Okay? And you might notice that, generally speaking, we satisfy Levine's test because all of our sig values are greater than 0.05, so we don't have any violations of our homogeneity assumption. We've done that many times before. And you might ask, well, why is that the case? Why are these all relatively safe? And the answer, again, is we defined our standard deviations the same way for men as for women. Right? There was all, for example, a standard deviation of 100 on the SAT score, or a standard deviation of 0.3 on some of the other variables. So those weren't differing between men and women, so we wouldn't expect to see much of an outcome difference here on the equality of variance measure known as the Levine test. Okay, let's now get down to where we might begin to unpack our MANOVA, which we now know is non-significant. And if you'll join me with dropping all the way down past corrected model, past intercept, to the variable of interest. We're doing this one analysis, this MANOVA on the gender group, and now we can see the F value for each of the independent, each of these outcome variables independently. Okay, separately, we can see that if we had just run a simple ANOVA or a t-test, we would have gotten this F value as ANOVA for SAT, that value for high school GPA, and so on down the line. Okay? So what's cool about this is sometimes you do wind up with a significant MANOVA, but you can't tell what's driving that. And so you can begin to unpack it by looking at these individual components here. Okay? And then one last bit, we can look at the grand means for each of those variables. And then we can disaggregate those grand means by saying that if you looked at SATs, here are the means again for group 1 and group 2, gender 1 and gender 2. Here are the standard errors, and SPSS automatically computes our 95% confidence interval. Who's okay with all of that? Can we try one more? We've got about 4 or 5 minutes, and we now know the clicks. If you'll join me by going over one more time to Excel, and now we'll go to the next tab, which is laid out in almost exactly the same way, except you might notice that the tab is labeled higher scores for gender 2. So what I'm going to do now is go into something like the SAT scores, and they're computed just like they were a moment ago, but now I've put in a conditional statement that I won't ask you to put in tomorrow, but I might ask you to copy and paste tomorrow. And I might say something like, if the gender is a 1, then assume that the mean SAT score is 500, but if it isn't, then assume that the mean SAT score is 510. Okay, so I've now made a conditional statement there where I've made the two different in a way that is contingent on gender. Who's following that logic? Even if you don't follow the syntax, you follow the logic. And so we're jacking up one of the two, and we're making higher scores for gender 2 across the board. Okay? So one last time, if you'll join me by clicking on P1, and we'll go all the way downstairs. We'll hold the Shift key, and we'll grab through L301. It's a really, really big file. Sometimes either Excel or SPSS will spaz out on a file this size. We'll do a Control-C to get the ring around the rosy going. Okay? And when you're set, why don't we paste over the data that we had a moment ago, and now we've stacked the deck a little bit using this, and we'll do one more MANOVA, and we'll call it a day. So we'll go back to our data set. We'll go to P1. We'll do Control-V, do it very deliberately, and just give it a moment. And you'll see your SAT score will change eventually. And at 9:58, it does take sometimes like 10 seconds. There it goes. It winked once at me. Now I'm at 7:02. So it does take about, maybe 10 or 15 seconds to take all that data, because it's a much bigger data set, but hopefully you get a new set of data in there. How many people have that newer data set ready to go? Yeah? Okay. So now we'll do one last MANOVA. We're still comparing the two genders to each other on 10 different variables, but we've stacked the deck at least a little bit to hope to get a chance now using MANOVA to find a difference between gender 1 and gender 2. So again, that was analyze, general linear model, multivariate, and everything is already set up in our options, so we don't need to change those. We can click one last time, okay? And we get some output over here, and I'll just wait to make sure everybody has that output. How many people have the second set of output? Yeah? Is that working for us? Okay. And why don't we do this? Why don't we drop right on down to the multivariate test? I'll go down there with you, and I'm going to take a look at my Wilks lambda, and I still wound up non-significant, but you might have wound up significant. How many people have a Wilks lambda that actually has a sig value less than 0.05? Did anybody get it? Okay. So several of us got it. Some of us did not. When I stacked the deck a moment ago over in Excel, I made very, very slight differences, like a 10-point difference in SATs, a tenth of a point difference in GPAs and so forth, so that we're now favoring the one gender, but only marginally so. And some of us are going to wind up significant, some of us are going to wind up non-significant. Who's following that? Yep. Okay. And so Wilks lambda is how we begin to interpret the MANOVA. And then if we want to unpack it, we can dial down, as we always do. And we can see which particular measured variables were driving the significant difference that we may have observed at the level of the uber variable, the latent variable. Okay. So that should take us through to tomorrow's quiz. Just as a reminder, we've done factor analysis previously, and there's a factor analysis data set out there that you can play around with. Okay? You can play around with this data set here for MANOVA. You can make one of those variables a covariate, as we've done before for ANCOVA, and you can practice on the signal detection theory, and that should fill us up for tomorrow. All right, thanks for a great session, and I look forward to seeing you tomorrow morning. And remember, tomorrow morning is our 8 o'clock morning, right? Not 8:30, but 8 o'clock. Special treat, right? Not only a quiz, but a quiz at 8, half hour earlier. See you there.